In this video, we're going to talk more about what is the time constant is, a graphical interpretation, and really just what it means and affects in the problem that we're talking about. So just like in the previous video, we're dealing with these first order linear differential equations, and we automatically will have this solution here, k1 plus k2 e to the negative tau. That's our standard answer is going to be for all of these first order circuit problems. Now, we're just going to simplify things a little bit nicer for our graph here and get rid of this k1 term. We're going to assume it's 0. So we're going to have k2 e to the negative t over tau. And also for simplicity's sake, I'm going to assume that k2 is a positive number for the graph below. All of this still works with negative numbers. It's going to look a little different. And then let's see what happens here. If we plug in 0 into our function, we get the value k2. If we plug in 1 tau, 1 time constant, we get k2 e to the negative 1. If we plug in 2 time constants, we get k2 e to the negative 2, which is the same thing as k2 e to the negative 1 times e to the negative 1. And so what that means is each time we're going to go tau to the right, we are multiplying our y value by another e to the negative 1. Now e to the negative 1 is about, I have right here, 36.8% or 0.368. And so what that means is, let's take a look at the picture down here. If we start at the value k2 and we're heading towards 0, because that's what the limit is going to be here, then after we go to the right 1 time constant, this value here is about 63% of the way towards 0. Right? The new result is about 37% of the previous result. So that means in the total distance from k2 to 0, we've traveled approximately 63.2% of it, and there's still the remaining 36.8%. Now the thing is, we have a new starting point, and if we're going to go another tau over to the right, then what we will see here is we will see that once again we will move over and accomplish 63.2% of our goal there and only have 36.8 remaining, but it's of a new goal of the previous one, right? So initially we had to go all the way from k2 to 0, and then after that we only have to go down a smaller amount, but we're still going to go down 63% of that smaller amount. So each time we go tau to the right, we're going to go another 63%, another 63%, and so on. So if you combine that after 2 time constants, we will have essentially only 13% from the previous one to go. And if I do another third time constant, just multiplying by e to the negative 1 each time, we're down to about 5% left to go. And after 4 time constants, there is less than 2% to go. So if you go like 4, 5, 6 time constants, you're essentially all the way there. And for a lot of circuits that we're going to have, our time constants are going to be something like in the milliseconds. So that means if you wait even 1 second, that would already be many, many time constants, and you're essentially already into steady state there. So that's just the idea here. So again, time constant is if you move that much right on your graph, you will have accomplished 63% of how much movement you were supposed to go. So if you were supposed to start at 100 and you were supposed to end at 0, then going 1 time constant to the right, you will have done 63.8% of the total movement, and you're only going to have, sorry, not 0.3, you're only going to have 36.8% left to go. Similarly, if we looked at the case where the k1 wasn't 0, let's say we need to start at 50 and go down to negative 50 here. So it's the same, a total distance of 100. If I go one time constant, I will have gone 63.2% of the way there. So 63% of the 100 total distance would be 50, and then 13 more down, so we'd be at something like negative 13.2%. So the way this is going to work is you look at where are you starting from, where are you going to, what's the total distance I need to get there along the y values, and every time constant you go right, you are going to achieve 63.2% of the current distance you need to get there. This is the physical interpretation of what a time constant is. And so what this means is our transient response is going to be on the order of time constants. So after, again, 100 time constants, any transient response will have been long gone. So we're going to be on the order of maybe 5, maybe 10, even that's pretty extreme, time constants. That's how much time we're looking at to figure out what's going on in our circuit.